common log value of this input, which I'm right now not aware of? Yes. So what will I do? I'll try to recall that yes, this given input is really a random input greater than 1, but there are some inputs greater than 1 whose common log values are cakewalk to compute. For example, log 1 to the base 10 is 0, log 10 to the base 10 I know is 1, log 100 to the base 10 is log 10 square to the base 10, which is 2, log 1000 to the base 10 is log 10 cube to the base 10, which is 3, and so on. So 10, 100, 1000, 10,000 and so on are some easy values greater than 1 whose common log I can very easily compute. So I'll use these common log values to compute the common log value of this random input greater than 1. How? First task is to try to fit this given random input between any two consecutive positive powers of 10. You know 58.34 is greater than 10 and less than 100. That means my given input lies between 10 to the power 1 and 10 to the power 2. Clear? Take log to the base 10 throughout. That means take common log throughout. What do you get? You get that the common log value of my given random input lies between 1 and 2. That means what can I say for sure? If this value is strictly lying between 1 and 2, that means definitely common log of my given input will be 1 point something something something. It will definitely look like 1 point something something. That means if I have to break it up, I'll break it up as 1 plus 0 point something something. And that's it. 1 will be the characteristic and whatever this decimal part is, this will be the mantissa. I'm interested in the characteristic and I've got the characteristic as 1, bingo. That means this is the method to compute characteristic corresponding to any random input greater than 1. Clear? But wait, you know what? There is a hidden shortcut in this method. The moment we catch hold of that shortcut, it will be a matter of few seconds to compute the characteristic corresponding to inputs greater than 1. What is that shortcut? Let me put some light on it. Well, examine your input, okay? Your input is 58.34. Clearly, the input has an integral part, which is 58, and a fractional part, which is 0.34. Count the number of digits in the integral part of your input. So, input's integral part is 58. So, 58 means 5 and 8. 2 digits in the integral part. 2 digits in the integral part. 2 minus 1 is 1, which will be the characteristic. That's it. Yeah, it's so simple. And why is it happening? Because your given input has 2 digits in the integral part. That's why that input is lying between 10 to the power 1 and 10 to the power 2. Yes. That means its log value is lying between 1 and 2 and hence its characteristic is 1. Suppose your given input would have had 3 digits in the integral part. In that case, your input would have been lying between 10 to the power 2 and 10 to the power 3. So its log value would have been lying between 2 and 3 and hence 2 would be its characteristic, which is 3 minus 1. And therefore, this brings me to the result that if the integral part of your input has k digits, that means your input is lying between 10 to the power k minus 1 and 10 to the power k. Hence, its log value will lie between k minus 1 and k, and hence its characteristic will be k minus 1, which is 1 less than the number of digits in the integral part of your input. That's it. That's the shortcut. Okay, so we'll just count the number of digits in the integral part. Minus 1 will be the characteristic. That's it. In fact, this is also true in the reverse fashion. What do I mean? Suppose I give you characteristic of log n to the base 10 is 2. Some input n is there whose common log has characteristic as 2. That means this log value will be greater than or equal to 2 and strictly less than 3. Okay, that means what? That this common log value will actually belong to the closed interval 2 open 3. And this would mean that your input n is actually greater than or equal to 10 to the power 2 and is strictly less than 10 to the power 3. So I can say this n belongs to the interval 10 to the power 2 closed and open at 10 to the power 3. That's why it's true in the reverse fashion that if the characteristic of log n to the base 10 is k minus 1, that means this common log value is lying between k minus 1 and k. Here I have non-strict inequality, here I have strict inequality. Got it? This would further mean that n is greater than or equal to 10 to the power k minus 1 and strictly less than 10 to the power k. Got it? Easy, right? Now, before I talk about the second strategy, which is to compute characteristic corresponding to inputs between 0 and 1, let me tell you a wonderful application of this that we just studied. Okay, so let's say I ask you, how many digits are there in 2 to the power 5? Tell me. Well, this is pretty simple to compute. 2 to the power 5 is 32, so there are 2 digits in 2 to the power 5. Simple calculation. Okay. Suppose I give you that, tell me the number of digits in 2 to the power 8. Okay. Again, a bit difficult, but not that difficult to compute. This comes out to be 256. So you will say there are 3 digits in 2 to the power 8. Now I ask you how many digits are there in 2 to the power 10. 2 to the power 10 will again, yeah, okay, a bit difficult, a bit tedious, I should say. But again, it's easy to compute. It's 1024. Yeah. So that means there are 4 digits in 2 to the power 10. But what if I ask you how many digits are there in 2 to the power 100? Okay. Now this becomes a task, isn't it? This is something which really is going to take a lot of time if we start computing this value manually and then count the digits and then answer this question. So, to combat or basically to conquer such questions, we have this result from the characteristic corresponding to inputs greater than 1. It says that if the characteristic of common log of the input is k, then k plus 1 will be the number of digits in that input. So if you want to find out how many digits are there in 2 to the power 100, what you just need to calculate is the characteristic of log 2 to the power 100 to the base 10. Whatever that characteristic comes out to be, plus 1 will give you your answer. So what is the weight? Let's start. I'll take my input to be 2 to the power 100, okay? Fine, I'll first of all compute the common log of this input, right? If I don't have the common log, I can't get the characteristic, isn't it? So I'll compute the common log, okay? I know what will this happen? 100 will come here ahead of log, so I'll get 100 into log 2 to the base 10. Okay, log 2 to the base 10 is given to me in the question, so I'll plug in the value and this comes out to be 30.10. That means I can break it up as 30 plus 0.10, so obviously 30 is the characteristic. Okay, the moment I have characteristic of log n to the base 10, number of digits in n will be characteristic plus 1, that means 31 is the number of digits in the number 2 to the power 100. So it was seeming to be so impossible to calculate the number of digits in 2 to the power 100, but can you see how beautifully the characteristic property gave us the answer of number of digits in 2 to the power 100. Clear? Okay, so this was the application of characteristic corresponding to inputs greater than 1. Now allow me to teach you what is the strategy of computing characteristic of common log of an input when the input is sandwiched between 0 and 1. Again, let's take a look at the example. So this is some random input sandwiched between 0 and 1. I want to know the characteristic of log of this input to the base 10. That's my target. So to know the characteristic of it, I should first of all have this value with me, which I don't have right now. Okay, so what will I do? I'll try to recall some inputs between 0 and 1 whose common log value is really cakewalk to compute. For example, log 0.1. What is log 0.1? Log 0.1 to the base 10 is nothing but log 10 to the power minus 1 to the base 10, which obviously is minus 1. Similarly, log 0.01, this is nothing but log 10 to the power minus 2 to the base 10, which is minus 2. Similarly, log 0.001, what is that? log of 10 to the power minus 3, which is minus 3, and so on. So these are some inputs between 0 and 1 whose common log values we know. We'll use these values to compute the common log value of this random input between 0 and 1. How? Same strategy. First task is to fit in this between any two consecutive negative powers of 10. So I know that 0.0093 lies between 0.001 and 0.01. Yes. That means what? That means this is strictly sandwiched between 10 to the power minus 3 and 10 to the power minus 2. Right? Once this is done, take common log throughout. What do you get? You get that the common log of my given input is sandwiched between minus 3 and minus 2. Okay? Now this means what? If I want to write its common log value, it will look something like minus 2 point something something something. That means when I break it up into integral and fractional part, it will be minus 3 plus 0 point something something something. Isn't it? Right? That means minus 3 will be the characteristic, and whatever this fractional part comes out to be will be the Mantissa. So what have I got? I've got the characteristic of common log of this given random input between 0 and 1. But again, in this entire long method, there is a hidden shortcut of getting the characteristic. What is that? Wait, before I reveal that to you, let's understand how to compute the characteristic of this given input in a more explicit fashion. So this is an alternative way, okay? 0.0093 can be written as 93 upon 10,000. Yes, this is nothing but 93 upon 10 to the power 4. Leave one 10 as it is. So you get 10 into 10 to the power 3, which is 93 upon 10 into 10 to the power minus 3. So this comes out to be 9.3 into 10 to the power minus 3. This is my n. So if I want to compute its common log value, this will be log of 9.3 into 10 to the power minus 3. I know log of m into n is log m plus log n. So this will become log of 10 to the power minus 3 plus log of 9.3. This gives me minus 3 plus log of 9.3. Obviously, this is your integral part and this is your fractional part. You wanted the characteristic, and that's how explicitly you can get the characteristic. In fact, you are able to look at the Mantissa value also very clearly. It's logarithm of 9.3 to the base 10. Now, this is something you don't have to run behind calculating right now. You learn how to compute these log values using your log table later on. Okay, so right now you don't have to bother much about it. But yeah, this is the explicit way in which you can actually look at log n to the base 10, which is minus 3 plus log of 9.3 to the base 10. Again, you are getting the characteristic as minus 3 only. Okay, so this was an alternative fashion to get the characteristic I wanted to discuss with you. So let's come back. Let's come back to what we had got. We had got minus 3 to be the characteristic. And as I was telling you, there is some hidden shortcut here, okay? And I'm really interested in catching hold of that shortcut because I don't want to invest so much of my time again in calculating the characteristic for inputs which are between 0 and 1 using this particular methodology. What is that catch? What is that shortcut? See, you know what? Count the number of zeros between the decimal and the first non-zero digit in your input. Look at your input. You have a decimal and you have the first non-zero digit after the decimal, which is 9. So count the number of zeros between the decimal point and 9. Right now I have 2 zeros. So minus of 2 plus 1 will be the required characteristic. Minus of 2 plus 1, that means minus 3, and that is what you're getting. So suppose I give you 0.00063005. Suppose this is my random input between 0 and 1 and I want to find the characteristic corresponding to this input. So what will I do? I will not again repeat this entire methodology to compute the characteristic. Rather, I'll just look at the decimal point and the first non-zero digit after the decimal point, which is 6. Count the number of zeros between this decimal point and 6. I have 3. So minus of 3 plus 1, which is minus 4, will be the required characteristic. So if you have any input between 0 and 1, any random input between 0 and 1 if you have, then just count the number of zeros between the decimal and the first non-zero digit after the decimal. Suppose there are k zeros, then minus of k plus 1 will be the required characteristic. Got it? Interesting, isn't it? Well, this was all about characteristic and mantissa. These were the two terms associated with common logarithm. I hope you had fun learning about them, isn't it? Well, technically this brings me to the end of logarithm. Yes, and that means we are through with all the 4 concepts in fundamentals of mathematics: sets, inequalities, modulus, and logarithm. Okay, so fundamentals of mathematics right now technically is over. But you know what, instead of winding up the session here, I thought why not devote some time in applying all that we've learned in these 4 concepts in some amazing questions. So let's get started, isn't it? At the end of the day, practice is what makes a man perfect, isn't it? So let's start with the first application. It's this question we have to solve. It's a logarithmic inequality. Look over here. What do you have? Log of some input involving x to the base 3 greater than or equal to 0. The good thing is there is no variable x in the base. I just have variable x in the input. You know the strategy, okay? First of all, I want to find out those values of x for which my input is a valid input. Because if the input is not a valid input, the left-hand side of this complete inequality won't even exist. It won't even be defined. So my first step is to find set A, which is the set of all those values of x for which my input is positive. Yes? Clear? Right? Because only positive inputs are valid inputs for log. I know that. Next task is to compute the set B, which is the set of all those values of x which satisfy my inequality. Okay? So because I want the left hand side of my inequality to exist and I also want my inequality to be satisfied. So what will I do? In the end, I'll take the intersection of A and B and that will be my final solution set. Right? So let's first compute A and then compute B. In the end, we'll take their intersection. Got the drill to solve this question? Let's start. Firstly, I want those values of x for which my input is positive. That means this expression is positive. Now, please examine this expression carefully. It is involving mod. I know mod of any real quantity is always non-negative. That means this mod of x square minus 4x is greater than or equal to 0. This 3 is obviously positive. That means what is it that I'm getting? What is it that I'm getting? The numerator is certainly positive. Non-negative plus 3 is always positive, right? Now look at the denominator. You know that x square is always non-negative. Mod of x minus 5 is also always non-negative. That means I am having a doubt. Can my denominator be ever equal to 0? No. Why? See, x square is 0 when x is 0. But when x is 0, mod of x minus 5 is not 0. Yes. So when this is 0, this is not 0. Right? Further, mod of x minus 5 is 0 when x is 5. But when x is 5, x square is not 0. So when this is 0, this is not 0. That means simultaneously both these quantities will never become 0. That means the denominator will always be positive. Okay, the denominator will always be positive. So what are you getting? Numerator always positive for every real x. Denominator always positive for every real x. Positive upon positive is positive. That means your input is positive for every real x. That means set of all reals is my set A. Okay, so my inequality, the left hand side of my inequality is actually defined for every real x. Cool. Now my second task is to actually find out the values of x which satisfy my inequality. So I want those values of x for which log of my input to the base 3 is greater than or equal to 0. But recall the graph of log to the base 3. Well, log is greater than or equal to 0 when the input is greater than 1 or equal to 1. Isn't it? That means log of input to the base 3 will be non-negative when the input is greater than or equal to 1. So now I want to find those values of x for which my input is greater than 1 or equal to 1. Let's simplify this left hand side part of my inequality, okay, because I want to solve it, right? Fine. So if I look at the numerator, I can write it as x into x minus 4, isn't it? And then I know mod of the product is product of the mod. So in next step, I can write it as mod x into mod x minus 4. Clear? I'm trying to simplify as much as I can. Now, wait a second. I know that this denominator is always positive for every real x. I just justified. So I can without any doubt cross multiply this over here without affecting the inequality sign at all. Right? When you multiply both sides by a positive number, the inequality sign doesn't change. And I know that this quantity for every real x is positive. So I can multiply both sides of this inequality by this particular quantity. It won't affect my inequality sign. And this is what I will get. So this is the maximum. I have simplified my expression and I want to solve this for x. So let me name this as my star inequality, which I have to solve. The problem with this inequality is that there are mod expressions involved, that too 1, 2, 3 mod expressions. I know mod function is a branch function. It behaves differently about its critical point, isn't it? That's why what do? We plot all 3 mod functions' critical point on the real line. So this function's critical point is 0, this mod function's critical point is 4, and this mod function's critical point is 5. So I'll plot 0, 4 and 5. The moment I've plotted the critical points, these 3 points have divided my entire real line into 4 distinct or 4 disjoint regions. First is all real numbers less than or equal to 0. Second is all real numbers greater than 0 less than equal to 4. Third is all real numbers greater than 4 less than equal to 5. And fourth is all real numbers greater than 5. What will I do? I want to find those values of x which satisfy my star inequality. Yes. But the problem is that I have got 4 regions. So what will I do? I will solve this star inequality in the first region, in the second region, in the third region, in the fourth region. Yes. And I will get 4 solution sets corresponding to these 4 regions. Okay. In the first region, how many values of x satisfy my star inequality? In the second region, how many values of x satisfy my star inequality? In the third, how many? In the fourth, how many? And in the end, I'll take their union, and that will be the set of all values of x on the real line which satisfy my inequality, which will give me my set B. Got the approach? So now let's get started. I have to find out firstly those values of x which are in the first region and satisfy my given inequality. Cool. So right now I am in my first region, all real numbers less than or equal to 0. Okay. In the first region, if x is less than or equal to 0, mod x will become x minus x. If x is less than 0, that means it is also less than 4. So mod of x minus 4 will become minus of x minus 4. If x is less than 0, it is obviously less than 5. So mod of x minus 5 will become minus of x minus 5. So I have got the precise definitions of each of these mod functions in my star inequality. That means my star inequality transforms to this. No more mod. Vertical bars you are able to get, right? So this is an algebraic inequality, very easy to solve. Simplify. What do you get? That x is less than equal to minus 2 by 3. Now x less than equal to minus 2 by 3. Minus 2 by 3 will be somewhere here. Less than equal to minus 2 by 3. That means out of all the real numbers in the first region, only the ones which are less than or equal to minus 2 by 3 are able to satisfy my inequality. So the solution set corresponding to the first region is coming out to be this interval. Got it? Now similar approach for the second region. Okay. That's the region I am in. When x is greater than 0, less than equal to 4. Now in this region, if x is greater than 0, mod x will become x. Yes. And if x is less than 4, that means mod of x minus 4 will be minus of x minus 4. If x is less than 4, it's obviously less than 5. So mod of x minus 5 will become minus of x minus 5. So what did I just get? I got the precise definitions of all these mod functions in my star inequality. So that means my star inequality will transform into this. Again, no more vertical bars. All I have is a simple algebraic inequality to solve, right? And we've solved inequalities, right? Simplify this, what do you get? you get a quadratic inequality. You break the middle term and these are the two linear factors, right? Now, obvious next step is to use your wavy curve method, isn't it? So on your real line, I am going to plot the critical points. One is x equals half and one is x equals 2. And now, wavy curve method, okay, plus, minus, plus. What about the critical points? Because it is less than or equal to 0, that means both the critical points will be included in my solution set. I want less than or equal to 0, so I'll have closed interval half to 2 coming over here. What was my second region? Can you recall? My second region was all real numbers greater than 0, less than equal to 4. And half to 2 is, yes, somewhere lying here only. That means what? Out of all the real numbers in the second region, only the real numbers which are lying between half and 2, including half and 2, are able to satisfy my inequality. So this is the solution set corresponding to the second region. Now, similarly, third region. Okay, when x is greater than 4, that means it's obviously greater than 0. So mod x will be x. Mod x minus 4 will be x minus 4. And because it is less than 5, that means mod x minus 5 will be minus of x minus 5. Again, the moment you've got the precise definitions of the three mod functions in your star inequality, what does your star inequality transform to? Just this placid algebraic inequality. No more vertical bars to create any confusion. And just simplify this. It's very simple. You get x less than equal to minus 2 by 3. Wait a second. You are in the third region. That means out of all the real values of x, greater than 4, less than equal to 5, what are the ones which are able to satisfy my star inequality is the question. I am getting x less than equal to minus 2 by 3. Well, minus 2 by 3 lies here. It's no real number less than equal to minus 2 by 3 is actually lying in the third region. That means what? No real number in the third region is able to satisfy my star inequality. So I get phi as the solution set corresponding to the third region. Did you understand? Yes, because from here I was getting all real numbers less than or equal to minus 2 by 3, but these real numbers don't even lie in the third region. That means there is no real number in the third region which satisfies my star inequality. So corresponding to third region, the solution set is empty set, null set, phi. Let's move on to the fourth region. When x is greater than 5, then obviously x is greater than 0. So mod x is x. If x is greater than 5, it's obviously greater than 4. So mod of x minus 4 is x minus 4. And if x is greater than 5, mod x minus 5 is x minus 5. That means I've got the precise definitions of all these mod functions in my star inequality. So my star inequality again transforms to an algebraic inequality, which when I simplify, I get x is less than equal to 8 by 5. 8 by 5 is what? 1.6, right? So 1.6 will lie somewhere here. I'm getting all real numbers less than 8 by 5 or equal to 8 by 5. But wait a second, we are in the fourth region. Fourth region is all real numbers greater than 5. That means what? There is no real number greater than 5 which is able to satisfy my star inequality. Because in case 4, we are getting the values of x to be less than or equal to 8 by 5. And no real number less than or equal to 8 by 5 lies in my fourth region. That means there's no real number in the fourth region which satisfies my star inequality. That means again, the solution set corresponding to the fourth region is coming out to be phi. Bingo. The moment I have found out what all values of x in the first, in the second, in the third, in the fourth region are able to satisfy my star inequality, I'll take the union of all and I'll get the set of all values of x on the real line which satisfy my star inequality. So I've taken the union. Union comes out to be what? This, right? Phi makes no sense in the union, isn't it? So I have this union, this. That's my set B. Yes. Remember what was the drill in the end? Final solution set is nothing but A intersection B. A is all the values of x for which the left hand side of my inequality was defined. Yes. B is all the values of x for which my inequality is getting satisfied. I want both things to happen. So A intersection B. Right? A intersection B is set of all reals intersection B, which obviously is set B, which is this. Clear? Yes. So set B comes out to be the final solution set for this inequality. I hope you found this problem very interesting and the correct answer is option A. Let's now check out this second question, okay? In here, again, you have an inequality to solve. It's logarithmic inequality. Quickly solve this and tell me the answer. Which out of the four options represent the correct solution set for this given inequation? Okay? Let's see who gives the answer first. In here, let me see how to solve this question. See, whenever you have an inequality with you, before directly jumping on to getting its solution set, first of all, try to catch hold of those values of x for which the left hand side and right hand side expressions are defined. First of all, I want the expressions in the inequality to be defined, and then I will run behind solving it. Always. So look at the left hand side expression, okay? It has log x to the base 2. Log of an input is defined only when that input is positive. Because I have x sitting in the input, the restriction comes on x to be strictly positive. Only when x is strictly positive will log x be defined. Another observation here is log x is sitting in the denominator. I know 1 upon something exists only when this something is non-zero. So right now for 1 upon log x to the base 2 to exist, I want this log x to be non-zero. Log of an input is 0 only when that input is 1. So I don't want x to be 1. Only when x is greater than 0 and not equal to 1 will this left hand side expression exist. Also, only when x is positive and not equal to 1 will the right hand side expression also exist. That means it's only for these values of x that my LHS and RHS are actually existing. Now I want to find those values of x which are satisfying my inequality, but make sure out of only these values of x for which my expressions individually are existing, I want to find out those values of x which are satisfying my inequality. Okay, right? That means out of all the real numbers strictly positive and not equal to 1, I want to find out which ones are there or what are the real numbers which are satisfying my inequality. Now, if you're sure that x is greater than 0 and not equal to 1, that means it's not equal to 0, not equal to 1, and it is not negative. That means it's either lying in the first region or second region. That means it's either strictly greater than 1 or it is strictly sandwiched between 0 and 1. So I will solve this question in two cases. First, out of all the real numbers in the first region, I will find out those real numbers which satisfy my inequality. So this will give me the solution set corresponding to the first region. And then out of all the real numbers in the second region, I will find out those values of x which satisfy my inequality. This will give me the solution set corresponding to the second region. Okay, in the end, I'll take their union and that will be my final solution set. So did you understand what did I do? I first of all found out those values of x for which my expressions were defined, which came out to be the set of all x greater than 0 and not equal to 1. That means it came out to be the set of all those x which lie in the first region or the second region. And then I am computing the solution set corresponding to the first region. Then I'll compute the solution set corresponding to the second region. Then I'll take the union and that will be the final solution set. Okay, right? So let's begin. Case 1. When x is greater than 1. Let me do one thing. I'll call this log x to the base 2 as a and this as b. If x is greater than 1, recall the graph of log x to the base 2 or log x to the base a when a is greater than 1. See, when input is greater than 1, log is strictly positive. So when x is greater than 1, log x to the base 2 is strictly positive. So I've got a is strictly positive. Now if x is greater than 1, I can say x plus 2 is greater than 1 plus 2. That means x plus 2 is greater than 3. That means root over x plus 2 is greater than root 3. Root 3 is 1.7 something, which is greater than 1. So I can say root over x plus 2 is greater than 1. If root over x plus 2 is greater than 1, that means log of root over x plus 2 to the base 2 is also greater than 0. When input is greater than 1, its log is greater than 0. That means from here I got that b is also greater than 0. Yes. So a is positive, b is positive. My inequality is 1 upon a less than 1 upon b. If 1 upon a is less than 1 upon b and a and b are positive, in the next statement I can write a is greater than b. Isn't it? We've studied this in inequalities. 1 upon a is less than 1 upon b. A and b are positive. That means in the next line I can write a is greater than b. Clear? Right? The inequality reverses. Cool? A is greater than b. Now, what do I have? Log of the input x is greater than log of the input root over x plus 2. Base is 2, 2 is greater than 1. I know log to the base greater than 1 is a strictly increasing function. So whatever is the relationship between the input, same as the relationship between the output, or whatever is the relationship between the output, same as the relationship between the input. I increase my input, my outputs get increased. I decrease my inputs, my output get decreased. So if log of x1 is greater than log of x2, this means x1 will be greater than x2, or x will be greater than root over x plus 2. We are in the case when x is greater than 1. That means this is positive, this is positive. That's why I can square both sides. My inequality will not get affected at all. So I get x squared is greater than x plus 2. This is simple algebraic inequality. You simplify, factorize. What do you get? Well, right now I'm in a situation to use my wavy curve method. So I'll plot the two critical points, 2 and minus 1. And now use your wavy curve method. It will be plus, minus, plus. Because it is strictly greater than 0, I will not include any of my critical points. I want greater than 0. That means all real numbers strictly greater than 2. Union all real numbers strictly less than minus 1 will come over here. But this I am not taking. Why? Because the case is that out of all the real numbers strictly greater than 1, find out those real numbers which satisfy my inequality. So out of all real numbers strictly greater than 1, only these are the ones which satisfy my inequality. That's why only 2, infinity will come as the solution set corresponding to case 1. Got it? Yes, very nicely. Now, let's solve the same inequality corresponding to case 2. That means when x is strictly sandwiched between 0 and 1. Now see, again, this is my A, okay, and this is my B. See, if x is sandwiched between 0 and 1, that means log x to the base 2 is strictly less than 0. That means I'm getting my A is negative for sure. If A is negative, that means 1 by A is also negative. Yes, that's obvious. Now, if x is between 0 and 1, x plus 2 will be between 2 and 3. So, root over x plus 2 will be between root 2 and root 3. Root 2 is like 1.4 something. Root 3 is like 1.7 something. That one thing I can say clearly, that root over x plus 2 is definitely greater than 1. Yes, it's greater than 1.4. It's less than 1.7. That means definitely it's greater than 1 for sure. If it's greater than 1, that means log of this root over x plus 2 will be greater than 0. If input is greater than 1, its log is greater than 0. So from here I'm getting b is greater than 0. If b is positive, its reciprocal is also positive. So what are you getting? You are getting 1 by a is negative, 1 by b is positive. Your inequality is this. This is 1 by a and this is 1 by b. According to the case you are in, you want to find out those values of x for which 1 by a is less than 1 by b between 0 and 1. How many x are there between 0 and 1 for which 1 by a is less than 1 by b? Wait a second. 1 by a is negative, 1 by b is positive, and a negative quantity is always less than the positive quantity. That means this inequality is being satisfied for every real number in case 2. Yes, that means case 2 solution set is complete case 2, which is 0, 1 open interval. So final solution set, case 1 union case 2, which is 2, infinity, union 0, 1, and this is my final answer. Sitting as option C. Quickly tell me how many of you all got option C as the correct one, because if you've got this correct, trust me, your concepts are really clear. You can feel good about yourself. Now let's check out this question. Now in here I have again an inequality. Okay. Well, you have to tell me which are the 4 options represent the correct solution set for this inequality. Okay. Come on, please get started. I'll also start solving this. Here I can observe one thing very, very interesting. I have x sitting in the input and I also have x sitting in the base. That means just by observing this fact, I can impose restrictions on x for sure. See, x is sitting in the input, so x has to be strictly positive for sure. And because the same x is sitting in the base, it has to satisfy the base restrictions of being positive and not equal to 1. So bingo. These are the restrictions on x for sure. It is for these values of x which are greater than 0, not equal to 1, that my left hand side is a valid expression. So first of all, I worked on finding out those values of x for which my expression is actually defined, it is existing. Now, out of these values of x which are greater than 0, not equal to 1, I am interested in the values of x which satisfy my inequality. So mind it, in my solution set, I will not accept x which is less than 0 or x which is equal to 0 or x which is equal to 1. Out of the x which are greater than 0 and not equal to 1, I want to find out what are those values of x which satisfy my inequality. Okay, right? So in here we can proceed like we proceeded in the previous question, but one catch is here in this question. What is the catch? When you look at this inequalities expression, I personally feel I can simplify this a bit. Can you see 3 over here and 27 over here, and I know 27 is 3 cube. Let's try to first of all simplify and then we'll jump on to solving it. Okay, obviously a simplified expression is much easier to tackle. So let's simplify as much as we can, keeping in mind that x is only allowed to be greater than 0 and not equal to 1. Cool, not a problem. Now log 27, first of all, I'm desperately waiting to write it as 3 cube. The moment I do that, I know this 3 will jump ahead and come over here. Okay, this is what I get. And now the situation is that here I have x in the input and here I have the same x in the base. Now I'm sure you would agree with me that watching x in the input is a much better situation than watching x in the base. Yes, you agree, right? So somehow I'll try to get rid of this x in the base. In here I have base as 3, so why not we try to create a common base? So instead of log 3 to the base x, I want to write it as something to the base 3. Instead of base x, I want base 3, so I'll use my change of base formula. This will be log 3 to the base 3 upon log x to the base 3. Okay, log 3 to the base 3 is nothing but 1, isn't it? So that's how log 3 to the base x gets converted to 1 upon log x to the base 3. You could have directly also done that. You know log a to the base b is reciprocal of log b to the base a. So log 3 to the base x is reciprocal of log x to the base 3. Okay, now that I have this, can I simplify this even further? Well, I'm pretty greedy of simplifying, okay, because I want to solve a very easy expression, an easy inequality. So that's why I'm running behind simplifying it as much as we can. Here I can take out, definitely I can take out the LCM. See, one thing should be disturbing over here, that is this denominator definitely non-zero? Is that happening or not? Did we ensure that or not? See, x is positive, not equal to 1. Yes, you know log is 0 only when the input is 1. So if the input is not allowed to be equal to 1, that means log of x is not allowed to be equal to 0. So I am pretty confident that my denominator here is definitely not 0. So I can keep playing with it. Okay, it is very comfortably sitting in my denominator. I have no problem with it. Now in here, what you can observe is that in your entire expression, you have log x, and constants otherwise. So let's take log x as t. And now my inequality becomes t square minus 3 whole upon t less than 2. Okay, this is pretty simple to solve. I'll bring my 2 on the left hand side and try to simplify this expression as much as I can. What do I get? Here is my quadratic expression in t. So I break the middle term, factorize it, and this is what I get. And now, of course, I'm in a position to use my wavy curve method. My critical points are 0, 3, and minus 1. So obviously use your critical point. Because it is strictly less than 0, I won't include this, won't include this, won't include this, plus minus, using my wavy curve method, okay? I want less than 0. That means I want this as well as I want this. Clear? But wait a second. My x is allowed to be only positive, not equal to 1. But here, I'm not getting values of x. I'm getting values of t. So t is yes allowed to be in minus infinity comma minus 1 open interval. That means this region or this region that is between 0 and 3. What was my t? T is log x to the base 3. Mind it, your solution doesn't stop here. You want to find the values of x which satisfy your inequality. You don't want values of t. Okay, so replace back your t, it is log x to the base 3. So you're getting log x will be less than minus 1 or log x will be between 0 and 3. Log x can take any real number as value, right? Isn't it? So that means log x will be less than minus 1 or log x will be between 0 and 3. Again, I don't want values of log x, I want values of x. So now I will find out what are the values of x, positive and not equal to 1. Keep that restriction in mind, for which my log x is less than minus 1. And I'll also find out what are the values of x positive and not equal to 1 for which my log x is between 0 and 3. Union of them will give me my solution set. So let's take the help of the graph. Well, this is the graph of log x when the base is greater than 1. Right now we have base 3 greater than 1. Okay, so first of all, I want this. For what values of x log x is less than minus 1? First of all, find out for what value of x log x is actually equal to minus 1. This is equal to minus 1 when x is equal to 3 to the power minus 1. That means x is 1 by 3. So when x is 1 by 3, log x to the base 3 is minus 1. If you want log to be less than minus 1, that means this you want. That is happening corresponding to all values strictly between 0 and 1 by 3. Okay, so corresponding to the first inequality, you found the solution set. Clear? Now, next. I want those values of x for which log x is greater than 0 and less than 3. I know log x is equal to 0 when x is equal to 1 and log x will be equal to 3 when x is equal to 3 to the power 3, which is 27. That means when your input is 27, your log value will be 3. And when your input is 1, your output is 0. If you want your log to be between 0 and 3, let me rub this. Okay, so now I don't need this. If you want your log value to be between 0 and 3, that means you are interested in this part of the graph. So log value is between 0 and 3 only when the input is between 1 and 27. Okay, that's it, bingo. What have I got? The solution set corresponding to the second inequality is all real numbers x between 1 and 27. So this gives you what? Open interval 0, 1 by 3, and this gives you what? Open interval 1, 27. Union of both will be my final solution set. In here, one thing you have to make sure that none of the values of x are violating the condition of being positive and not equal to 1. You can see all real numbers here are positive and not equal to 1. Clear? So out of all the positive real numbers not equal to 1, these are the ones which are satisfying my inequality, and hence they are making up my solution set, sitting as option C. So if you got option C as the correct option, you can pat your back and kudos, you've done a great job. Okay, time to tackle another question. Well, in here again I have an inequality. I have to solve this. Out of the 4 options, quickly tell me which do you think is representing the correct solution set for my inequality. Time being, let me start solving this. In here again, my first target will be to catch hold of those values of x for which this expression in my inequality exists as a real expression. It is defined. Okay, so I'm first of all interested in that. Okay, then I'll run behind solving it. Okay, now in here, what can I see? First of all, in the first factor is I have 2x as the base. So variable is sitting in the base. Base should satisfy the base restriction. That means the base should be greater than 0 and it should be not equal to 1. So this gives me x should be positive and x should not be equal to half. Only then this first factor or first expression will be defined. Next, in the next expression I have x in the base. So x has to be positive and not equal to 1. So another restriction added. And lastly, 4x I have. That means input has x. So 4x should be positive. That means x should be positive. I've already written. That means all these 3 expressions on the left hand side will individually exist and will individually be defined when x is positive, x is not equal to 1 and x is not equal to half. Clear? So obviously the entire left hand side will be defined when x satisfies all these restrictions. So now we are confined to only these values of x. Out of these values of x which are positive, not equal to 1 and not equal to half, I want to find out those values of x out of these only which satisfy my inequality. Okay, so any real number which is not positive or it is equal to half or it is equal to 1 will not be accepted in my solution set ever. Okay, now let's start solving this inequality under these restrictions. Cool? If I'm not wrong, before directly jumping on to solving it, I can see that I have some scope of simplification. So let's simplify this as much as I can. Again, the one thing which is really troubling me is x sitting in the base. Again, you would agree that having x in the input is much better situation than having x in the base. Okay, so I will try to make my base free of the variable. Okay, so if I don't want 2x or x to be in the base, what do I want to be in the base? Well, this one expression has 2 in the base, so let's make the base uniform throughout. Here I have log 2 to the base 2x, which will be reciprocal of log 2x to the base 2. So you can see how now my base is 2, it is not involving any variable. Clear? Similarly, look at this. It's log 2 to the base x, which is reciprocal of log x to the base 2. Again, you can see the base is 2. It is a constant. It's free from variable. So now, no more base involves variable. In fact, all the bases are uniform. It's equal to 2. So that's my final expression. Again, is there any more scope to simplify this? Well, let's see. Here I have 4 into x. Log of m into n is log m plus log n, so I can write this as log 4 plus log x. Similarly, here I have 2 into x, so I can write it as log 2 plus log x. Right? I know log 2 to the base 2 is 1 and log 4 to the base 2 is log 2 square to the base 2, which is 2. So this becomes 2 plus log x upon 1 plus log x whole into log x greater than 1. Clearly, everywhere what I can see is log x to the base 2 only. Yes, so why not take log x to the base 2 as t, and now my expression becomes 2 plus t upon 1 plus t whole into t greater than 1. Okay, let's simplify this. This is much easier to simplify. Okay, well, I'll bring the 1 to the left hand side. I want to create right hand side as 0, and I try to simplify this expression. Now here I have a quadratic factor. This will be t plus root 2 into t minus root 2, and here I have product of 2 linear factors already. So this I have simplified my left hand side completely, and now of course I'll use my wavy curve method. I'll plot on all the critical points minus root 2, 0 and minus 1. Because it's strictly less than 0, none of the critical points will be included in my solution set. And now wavy curve method, plus minus plus minus plus. I want less than 0, so t will lie here or here. Mind it, this is the range for t. I want the range for x. So don't stop your solution here. Okay? T belongs either here or here means what? T is nothing but log x to the base 2. So log x to the base 2 is strictly between minus root 2 and minus 1, or it is strictly between 0 and root 2. Now that I know this, I want to find out the values of x for which log x is between minus root 2 and minus 1, or log x is between 0 and root 2. So what will I do? I will solve this inequality for x and find the solution set. Next, I'll solve this inequality for x and find the solution set. In the end, take their union to get my final solution set. So let's take the help of the graph. Here I have log x to the base 2. Base is greater than 1, so this is how the graph is going to look like. Firstly, I want log x to be between minus root 2 and minus 1. So let's understand log x is equal to minus root 2 for what value of x? Okay, base is 2. Okay, x should be 2 to the power minus root 2. When x is 2 to the power minus root 2, log x is minus root 2. That means something like this is happening. This is minus root 2 and this input is 2 to the power minus root 2. Next, I want log x to be minus 1. Log x will be minus 1 only when x is 2 to the power minus 1, that means 1 by 2. So when this is 1 by 2, this is 1 by 2, in that case log x is minus 1. So if I want log x to be between minus root 2 and minus 1, that means this is the portion of the graph I'm interested in, which is coming corresponding to all the real numbers strictly sandwiched between 2 to the power minus root 2 and half. So if log x has to be between minus root 2 and minus 1, x will compulsorily have to be between 2 to the power minus root 2 and half. Clear? So this is the solution set for the first inequality. Now I'll solve the second one. I want log x to be between 0 and root 2. I know log x is 0 when x is 1, and now I want log x is root 2 when x is 2 to the power root 2. Clear? So let me rub this and now understand, okay? When x is 0, when x is 1, log x is 0, and when x is 2 to the power root 2, let's say here is 2 to the power root 2, in that case log x is root 2. So if I want log to be between 0 and root 2, that means this part of the graph I'm interested in, x compulsorily will have to be between 1 and 2 to the power root 2, and that's it. This is the solution set corresponding to the second inequality. Yes, got my point? Right? So this interval union this interval will be my final solution set. Got it? And one thing you can clearly ensure over here, that none of the real numbers x in my solution set are not satisfying the original restriction. My original restriction was x should be positive, x should be not equal to 1, x should be not equal to half. So there are no real numbers which are violating this restriction. And hence this is my final acceptable solution set. Got it? This is sitting in option C. How many of you all got it correct? Quickly tell me. Congratulations if you've got it correct. Okay then, I have many more good problems to solve, but time constrained, I'll have to wind the session up here. I agree that today the questions that we discussed were pretty much on a difficult end, but let's not lie to ourselves, okay? We have to increase our level of problem solving. Yes, if we want to perform well in the main exam. It's really better always to sweat in the training rather than bleed in the main battlefield. Okay, so don't run away or escape from these questions. If there was any point you were not able to follow while I was discussing these questions with you, or any concept where you were stuck at, be it from sets or log or inequalities or modulus, not to worry at all. Please don't panic. Just revisit that concept again and genuinely spend some good quality time with it. Trust me, it will forever be yours. You know, that's how it works, not just in human relations, but in studies as well. It's a give and take thingy. You give time and that will become your friend. Yes, you give time to that concept and that concept will, trust me, become your friend forever. And once that happens, any question which comes your way, how much ever challenging that is, easy, medium, hard, whatever category, trust me, you will be able to conquer it and the victory will be yours. Just remember, never give up. It's me, Bhumika, signing off. I'll see you very soon in the next class. Till then, you take care and keep learning. Thank you.